Hello everyone. I don't think anyone else has joined, so let's just wait.
Hello.
Hi Rohi, sorry I was talking on mute. Let me just share my screen and then we can continue. Krishna, 1 minute. Mm, Share case study, share. Okay, I believe I have not saved it with the right name. Let me just do that quickly because then we'll have confusion. I hope you can see it, right?
Yes.
Yeah. Okay. Okay. Then let's make a start. I believe others are going to pour in. So until yesterday, we have looked into two kinds of scaling: min-max scaling and standard scaling. We looked into some of the definitions and how to implement them. We looked into the fact that why we need to do that, and then we let's make a start with the scaling part. And then, if we can speed up a little bit, maybe we will touch base with multiple linear regression today itself, right? So let's go ahead. So to do this, what we are going to do, as simple as it sounds, I mean, theoretically it might have a lot of things to consider, but practically it is quite easy. So what we are going to do is that as simple as we need the libraries to do standard scaling and min-max scaling. So I've just gone to the top of the document as per what we plan to do. So from sklearn or scikit-learn, there's a module called pre-processing, right? So from this module, we are going to import min, max scaler and standard scaler, right? These are to be used for scaling the features, right? So I'll just do a control enter so that I can import the library. I believe they are imported now. So these are the libraries which are there. So one library for each. So a min max scaler is a class. Standard scaler is one more class. We are going to use them when we like them. Now, in the last session, we were talking about why or in which conditions we should use min-max scaler and in which conditions we should be using the standard scaler. I'll explain that in a little bit, but let's just quickly see if yeah. So what we are going to do now is that first of all, we are going to make the comment. So we are going to say 6 dot scaling of features, right? And then we can continue. So that question was a generic question, but where we really need this kind of specific kind of scaling is as simple as when min-max scaler will not work is when you have a lot of range of data or the dimension of data is very high or the variance of data is very high. We can see or we can look into those cases where min-max scaling does not really give good scaling opportunity because there is a lot to scale, right? And why it does not help us is because it is doing a lot of activities, or the computational activities are more as opposed to uh, the actual implementation itself. So it takes a lot of time, right? It takes a lot of time. Just a moment. It takes a lot of time. I'm sorry. It takes a lot of time to do the thing, right? So there are a certain, let's say, set of advantages and let's say disadvantages as well. Min-max scaling, as you see, min-max scaling is not putting any distribution, right? So it is not enforcing any distribution on the data, and that is really bad, because standard scaling, because it is using Z or the same formula as we saw in the Z score kind of thing. So that's why it is trying to enforce kind of a normalcy in the distribution of the data, which is very good because it is trying to make your data normal. Although, as we have already seen, X and Y may or may not be normal. They should only be related when we are doing linear regression. But if I have a data for which the distribution is actually normal, it really helps my algorithm to reach the minima very quickly, or to reach the conclusion very quickly. That is the main goal. The main goal is to have an algorithm which is as effective as possible, irrespective of how much data I have. Right. So the training part should not be taking a lot of time, because that's the only way I can create a very robust kind of a model which can be used with any size or any size of training data. And then basis the input that I give with respect to the testing data, I get the output. That's all I need to do. Right. So that is my main concern here. My main concern, first of all, is that in all cases, it's not going to work, because we do have cases where we are going to have a lot of range of data, hence it is going to take a lot of computation. And then again, we will have cases where we, if we apply min-max scaling, it's not going to enforce any distribution. That's why it is kind of, impacting the data to some extent as well, right? Now, this does not mean, or obviously this does not mean that just because this is happening, this does not mean that standard scaling is actually superior than min-max scaler. The answer is no. It is actually just a way of looking into things. So let's say you have a very good or a small sample of data, right? A manageable sample of data. Then you may most probably go with min-max scaling, because it is quite easy to understand. If you look at the formula as well, if you look at this Wikipedia page that I've shared as well, it will be very easy for you to relate that, right? But if you look at standard scaling, again, we are going back to those days of using Z value and all these things. And then we all know that whenever we start using Z scores, there is always been a confusion, right? So keeping the range of values to a certain extent, right? The one that min-max scaling is doing is good, right? In many cases it is good, but in many cases it is not good. So it's kind of complementary. One is going to complement the another, right? So we just have to keep them in mind before we take any decisions. But we cannot be inclined towards one as opposed to another, right? Because each one has its own advantages and the disadvantages, basis where we have a use of what we are going to use that. Okay, so fine, let's now try to find out, or let's now try to implement it. So again, I'm going to create the training data and testing data. Testing data I already have. The testing data, I don't need to do anything with it. I have to look into the training data, right? So training data has to be scaled first, and then we can look into testing data and all these things. Now, there is one thing to be very clearly understood here. Just because I am using the training data to do the scaling does not mean that we will only be doing feature scaling. We can also do target scaling as well. So I'll quickly show you in this example how we do target scaling, and it is not a really bad thing to do, but usually we don't do that. Usually we don't do that because it is usually the features which is used to converge to y, right? Because y is equal to theta 0 plus theta 1x in this case of a simple linear regression. That's the reason why if I'm only concentrating on x, my job is done, right? But that does not stop you from scaling y as well. You may also try to scale y, because that helps in many algorithms, including multiple linear regression, not the simple one maybe, but in multiple linear regression, it will really help you to converge. It will really help you to find the best possible pattern within the data very well. So your R square will improve, your R square will be stable. The regression fit line or the regression line is really going to be very stable. right? So that's exactly what we can do over here as well. So what we can do is that, let's say I'm just going to take a data. I'm just going to take that same training and let's say testing data that we have already taken earlier, right? So let's start with this. So enter. Let's again prepare the training and testing data, and then we will scale it. Okay. So what I'm going to do, X train, Y, oh sorry, X test. Don't, is there any message? No. X train, X test, Y train, Y test should be found out from train test split. I input X, Y. And this time I'm just going to say train size is equal to 0.7, random state is equal to 101. Right? I'm just going to do that, and I've got my X train and X test. Now let's scale the training data first. Right. So why I'm saying the training data first, because now I'm going to scale both features as well as the target. So Y train will also be, Y train is also going to be scaled. All right. So I'm going to write this in a different kind of a naming. So let's say I'm going to call it X train scaled. Right. I'm going to create X train scaled. But then, as you know, this is a simple linear regression, right? So in case of a single linear regression or simple linear regression, we have already seen that we have to do the value reshaping, right? The process of scaling only applies on a 2D array, right? And in this case, it can be applied on a 2D array only if we are going to do a value reshaping similar to what we have done earlier. So in earlier cases, what have we done? We have simply taken X train, then we have taken the values, and then we have said reshape, I believe was the name of the function, where we have input given like this, right? So this is exactly what we did to reshape it. The same thing I believe I can apply on Y train as well. I'm just going to reshape that. Okay, because I just want to ensure that I have 2D arrays in place, right? Now that I have 2D arrays in place, or okay, now that I have 2D arrays in place, let's finally scale the data. Okay, so to scale the data, what we are going to do, I'm simply going to say extend scaled. I'm going to keep the same name of the variable. Okay, I'm not going to make any confusions by making it different things. I'm going to keep the name as same, X train scaled and Y train scaled, and then I'm going to use something which is an object, which is my object of scalar. So I need to create that object first, right? So I say scalar is equal to, let's say in this case, I'm going to use standard scalar first. Okay, I'm going to use the standard scalar first, and then maybe I can use the min max scalar, and both we can look at, right? So extend scaled is going to be scalar dot fit underscore transform. Okay, this is the method that I can use to directly fit the data and then also transform the data. So fitting means I'm reading the data, I'm absorbing, I'm ingesting the data, or I'm understanding the data, the pattern in the data, right? And I'm simply trying to fit it with some kind of mathematical formula. And the moment I say transform, that mathematical formula, in this case standard scalar, is being used, right? So the formula of z scale or the z score is going to be used over here, and then it is going to transform my data, which is going to be my input, obviously is going to be extend scale, right? So I'm simply inputting the same value, right? I'm inputting the same value, and then I'm trying to do this. So in this case, what I can do, let me just type this. So this will be Y train scaled, and this is going to change this to Y, right? So this is how I can scale. If I enter that row, I can scale both X train and Y train. And then I can also look at what is happening. Okay, so let's check, sorry, let's check uh, what exactly did we do as part of scaling, right? Okay, so I can say something like this, original, or I'll say mean of X train, or the training data, right? So I am taking the mean. I just want to take the mean and the standard deviation. Okay, mean of X trained scaled is equal to, okay, I'm just going to say NP dot mean, and then I'm going to take X train scaled, okay, and then I'm going to say home and enter, and then I'm going to say the standard deviation. I just want to find out what is the mean and the standard deviation. So I'm just going to put here std, and then if I run this, I'm going to see what is happening over here. You see, it is closer to 0, 1.14 to the power epsilon minus 16. So it is quite close to 0, right? The mean has become very close to 0, and the standard deviation is exactly equal to 1. So I've converted X train scaled into a normal distribution, right? A normal distribution is where mean is equal to 0, standard deviation equal to 1, right? Exactly the same thing happens if I look at y. So I'm just going to replace this with y, right? If I replace this with y, I'm going to get the value for y as well, and it will be similar, right? If I look at this, you see it is very close to 0, and then I have y train scaled. You can ignore the scale, right? This is minus, this is plus, it doesn't matter, right? It's not going to matter, because end of the day, what matters is this. It is e to the power minus 16, right? It is too small. This is also e to the power minus 16. So any value beyond this is nullified. It is very close to 0, and then the standard deviation clearly is equal to 1. So now that I have, just a moment, let me just save my notebook. Yeah. So now that I have my data scaled, okay, let's see what advantage it's going to give me. Is it really going to give any advantage in this case? You have to figure that out, because then ultimately, if there is no advantage, there's no point of doing scaling, right? When we are doing scaling so that we can find some advantage, right? Now, a very good way, right, is now what I'm going to do is that I'm going to now use, okay, I'm going to make use of the stats models. Okay, I'm going to make use of stats models so that, right, so that I can get that table output. I'm intentionally not using scikit-learn, because in scikit-learn it's like a black box. I'll not be able to understand how good or how bad internally it is working. Let's go back to stats models. We'll use stat model to fit this model again, create a new model using X train scaled and Y train scaled and so on. And then after fitting the model, we are going to look at the summary. If I look at the summary, I'll be able to understand what exactly is going on over there, and if it has added any benefit. Okay, if it has added any benefit, right? So let's prepare for stats model. I'll just write SM here. Stats model modeling. Okay, so before I even do that, let me just do one thing. I'll just add a new column, and I'm going to call this 7 remodeling after scaling. Okay, I should have also given some notes over here, so why not I enter another row and I say this. And as we see above, post scaling of the training data, we have achieved normal distribution. Okay, normal distribution for these data sets, right? Why? Because we have used standard scaler. Later on, we are going to use the min max scaler as well, and we are going to see how that is really going to work. Okay, but as of now, we have used standard scaler. We know standard scaler creates a z score, and that's why it is scaled in this way, right? Now, again, if I want to create a model, okay, I need to add that constant, where I have to add the constant to X train scaled. Right, you might be wondering why I need to add that constant, because I've already converted it into 2D array. That is correct, but I need to have that value here. The value of theta has to be initialized to 1. Okay, that is not done by the reshaping. Reshaping is simply converting a 1D array into 2D array. That's it. Okay, it's not adding any default value. Okay, so what I'm going to do, the function was what? Add underscore constant, right? I believe add underscore constant, and then I'm going to say X train scaled. Okay, this should do my job, right? And then what I can clearly say, linear regression with scaled data. Okay, LR scaled linear regression with scaled data is equal to SM. Okay, dot OLS, right? Ordinary least square is what we are going to use. We're going to pass y train scaled as the first variable, then x train scaled as the second variable, which to which we have added the constant as well now, and then we have to fit the model, right? So what we need to do, we are going to call the fit function over here, and the model is done, right? Now that the model is done, let's look at the summary or output of our model post standard scaling is applied. Okay, so how do you do that? LR scaled dot summary, right? We're just going to do a pretty print of that, and we're going to see what is happening over here. Now you can see what is going on. Let's take a pen. If you remember what happened earlier, if you look at the R square value, you can clearly see it has not changed much. It's closer to 0.8. Earlier might be it was like 0.82, now it is 0.81, doesn't matter much, right? Also, if we look at this value, okay, we can compare this value back. Yeah, we can go back and we can compare this value, don't worry. So what we can do basically is that, let me clear all the drawings and let me just come over here for comparison, okay, only. Okay, so I'm going to do LR summary, right? That model is still there, so I can print that. I think it was LR only, right? Or linear regression object has no summary. What was the model name? Just a moment. Let me see what model I've used. SLR. Okay, very good. SLR. So I'm going to say SLR, and I'm going to get this. Okay. So the first model, as you can see, it was like 0.812. You see over here, 0.812, 0.811. Okay. What is happening in the new model? Okay, it is almost exactly the same, right? It is almost exactly the same. There is not much of a difference over here. So the R square part is not changed. Okay, this is the first finding, right? We have to write these findings. So we are going to use our notepad, okay, to write these findings. Okay, or maybe we can write it over here in the notebook as well. First finding, scaling does not impact R square or adjusted R square, at least in case of simple linear regression. You have not seen what happens in multiple linear regression. You have not seen what happens with mean max scalar. With standard scaling, there is no effect on R square or adjusted R square value when it comes to simple linear regression, which has one feature, X, right? The second thing, okay, let's come down. Again, let's come down and let's try to look at this value. You look at this probabilistic F statistic value. Okay, it's like 7.93 e to the power minus 74. Fine, this is one value. If I compare this with this value, which value is smaller? This is epsilon to the power e to the power minus 52. That was e to the power minus 74. So this value is actually much smaller, right? So in the previous model, I have got a p-value which is actually much smaller than the p-value of this model. This may or may not be the case, but this is almost always the case. Okay, almost always, if you do a standard scaling, your p-value increases a little bit. Why? Because your data is now normalized, because it has a normal distribution. Now it is showing you even a better representation of the p-value. In the earlier case, because your data was not scaled, it was not showing you a very accurate implementation of p-value. Okay, please don't think that because we have scaled the data that using standard scaler, it has impacted my model. My p-value is increasing. Somewhere down the line, maybe it's going to be greater than the alpha value. Then my null hypothesis will have to be accepted. So that is not what I want. That is exactly not what I'm seeing over here, right? Just because the p-value in the new model is a bit more than that in the old model does not mean that my new model is bad. Okay, it really does not mean that my new model is bad. Okay, what we need to look for, okay, what we need to look for again is that I again go back over here and I try to see what is this table talking about. Okay, this constant, this TV, the coefficients and so on. If you look at the standard errors here, it's like 0.3 and 0.002. If you come over here, it's the same for both the cases. It is the same. Okay, it is the same. Again, the second observation, if you look at the p-value for constant, it is 1, it is more. Okay, it is more. It is more than the alpha value. 0.05 is the alpha value. Nobody has specified anything. So that's why I've taken 0.05 as the alpha value. The p-value for constant is actually more than the alpha value. That was not the case over here. Okay, the constant has to be considered. It is making a significant impact in my original model because the p-value is less than, much less than 0.05. But in this case, it's not. It's actually much higher than 0.05. That's why in my new model, the constant has no impact. The constant has no effect. Is that the right thing to do, or is that the wrong thing to do? Okay, depends on what your business context is or how you can try to decipher this. So example given, this is a case where on my x-axis, right, on my x-axis, I have my x value, which is my investments in TV. And on the y-axis, I have the sales figures, okay? If you look at this data over here, right, the data that you can see over here, right, this constant value is almost close to 0, e to the power minus 16. I'll consider this as 0. Right? So my theta 0 has become equal to 0. Then my equation has become what? My equation has become sales. Okay, sales is equal to some value, in this case that is 0.9016 multiplied by TV. Right? Because theta 0 has gone to 0. I can consider that as 0 because minus 2.151 e minus 16 is very close to 0. Hence I'll consider this as 0. This is my new model. Right? If this is the case, then my slope somewhere, this is my slope, right? Let's just try to approximate. Let's say that this is my best fit line, right? So the slope has come up to this. Now the question is, which model is better, right? Do we have any criteria to find out which model is better? Let's come down and see what was there in the earlier model. Okay, in the earlier model, this was the case. Okay, earlier model, constant 6.9748, TV 0.0555. Right? Now, I'm just going to write it over here once, just to do the comparative study. The old model said sales is equal to 6.97 plus, 6.97 plus 0.06, right? Or 0.555 multiplied by TV. Okay, that was my old model. Now, can any one of you guess or try to understand or try to tell me which model do you think is actually better? Do you think this model is good or do you think this model is good? There is no fine or a wrong answer. You can go ahead. I just needed to know what is your impression. I mean, which expression seems more good for you? Is this impression or this expression?
Well, if I have to choose, then I will choose the second one. 6.97 plus
Okay.
0.055.
Any particular reason, Rohi, why you are choosing that?
I'm not able to guess the exact reason, but I think that it will be the right one.
Okay. Okay. What about you, Sarang? Or did I delete the drawing or what? Shit. Okay. Fine. I think Sarangs is on mute. He's not able to speak, which is okay. So yes. So based on Rohi's answer, he thinks the second model is good. Okay, so model 2 is actually better. Let's just try to draw model 2. once quickly, and then we can see what is happening in model 2. Model 2 will look something like this. I'm not going to draw X and Y again. It's going to look something like this. Okay, let's say it is just like something like this. Okay, now if it is like this, and I have another model, I'll just quickly draw model 2. Okay, this is model 1, I'm sorry. Okay, this one is the original model. Okay, this is my original model. So this is original model, and this is my new model. Okay, this is my new model. Okay, and in the new model, what is happening is, if I take a line, if I simply draw it, the line, no, sorry, line has to pass through the origin. The line is something like this. Okay, maybe something like this, right? So this is the model. Now, how do I say which model is good? Is this model good or this model good? Right? It has to come from your domain expertise. It does not come from the numbers. That is exactly what I wanted to show over here. If you look at the numbers, you'll get confused. If you look at the p-values, right, you will get even more confused. Looking at the numbers, looking at the p-values is good because we have to interpret the model, right? We need the interpretation of the model. So you need the equations, right? Exactly. That is okay. But which model is going to be good? In this case, I'm trying to figure out if there is any effect of TV on my sales. And in the new model, it clearly says that if I don't invest anything on TV, my sales will be zero. Is that a practical scenario in my business context? The answer might be no. Because if you look at the data set, there are two other areas of advertisements where I have substantial investments. It may or may not be giving me good results. And exactly that is the reason why I'm doing a linear regression, right? I'm doing this regression analysis to figure out which feature is good for me, whether TV investment is good or radio or something else, right? Maybe tomorrow I'm going to add a new media, let's say social media. I'll go to Facebook and I'm going to purchase, let's say, paid ads, right? So that may well be another way in which I'm going to promote my materials or the subject or the product that I want to sell, right? In that case, explaining this to a business user is really going to be difficult. Why? Because the coefficient or the intercept is zero, right? The intercept is zero. This means the effect of investments on a TV budget or a TV based advertisement budget, okay, or ads that I'm going to show on TV, that budget is so supremely important that it doesn't matter whether I'm investing anywhere else in the context. Now you might be wondering why I'm considering the other areas if I have not taken that into the analysis itself. Right? In this case, I have a simple X, simple Y. X is equal to TV, Y is equal to X. I've not even taken the rest of the variables. Why am I considering? I'm considering it from a non-statistical point of view. I'm considering it from a business point of view. If you want to explain this model to any business person, any product owner, what are you going to say? If there is no investment in TV budget, there is no sale. If I put $0 in TV investments, there will be zero sales. Will the product owner agree? Will the owner of the product, will the business person agree? He might not. If I had been the owner of the product, knowing my business, I may not have agreed. Why? I would have challenged you to rethink this model again, because I have other places where I'm investing for advertisements. And I'm not going to believe they don't have any positive or negative. I'm not saying they'll always have a positive. They may have a positive impact, they may have a negative impact, but I am not going to believe that other places or other advertisements are not even having any impact, right? This gives you the opportunity to do multiple linear regression, and also gives you the opportunity to think about the original model, where you had TV and you had sales, and there was some intercept, right? This intercept at many business contexts is really very important. Why it is very important is because that gives you the scope to look for the variables or the attributes which are hidden, right? Which are there in the data, but you are not able to quantify it. That's why it is theta zero. Okay, theta zero is what? If you look at the equation, y is equal to, okay, let me just, I have a very bad mouse today, so let me just write it like this. So y is equal to theta 0 plus theta 1 multiplied by x, right? If this is my equation, right? If this is my equation, then this value is what? This is my intercept. Intercept is what? Intercept is basically something that does not account with x. The thing that accounts with x, or the property that relates to x, is t1, right? So y is related to something of t1, that is fine, but there will always be some other thing which is part of the equation which might impact my business, but that may or may not be true for every case, right? You have to be very specific and very critical here. Critical thinking is going to come into play. It's not only the numbers that you can use and you can solve the problem. That's a statistician's approach. Please don't do that. This is not statistics that we are trying to learn. We are trying to learn how to employ data science. In this domain, what we do, we get the numbers, we get the output, we get the statistics, we get the model, we get the analysis, everything we have got. Now we are going to do some intuitional decision making as well, even if the model is wrong. Even if the model is wrong, mathematically, the new model is actually better than the old model. Can you tell me why? Because in the new model, I don't have this factor at all. I don't have anything which is uncontrolled. I just have this factor, and I know that if I control x, this is always going to be constant, which if I remember, it was something like 0.9, right? So this stays a constant in my new model. I just have to manipulate the value of x, which I control. And there is a factor which is attached only with x. There are no unknown factors. And mathematically, hence the new model is actually a good model, right? This one is actually a good model mathematically, but original model is, in my point of view, in this case, it is just my point of view. If I was working in this analysis for my organization, I would have voted for the original model, where I have not done the scaling of data, where I have not used standard scaling, where I've got the coefficients like these, where I have got good p-values for both the cases. So both my theta 0 and theta 1 are relevant for my equation, for my regression. And I would have vouched for the original model, because at any point in time, practically looking at my business context, I might be taking a decision that the effects of other variables, which is defined by this intercept thing, which is over here, cannot be nullified. In my business context, it cannot be zero. Now, are there any situations where it can be zero? Yes. Yes, it can be zero. Why can't it be zero? Okay, give me 1 minute. It can be zero in cases like these. Let's say if I have a model which is something like this, and what I'm trying to plot, okay, what I'm trying to plot is the height that results into the weight of a certain individual. In this model, if I really am able to find out a linear relationship, okay, although if you look at it from a biological point of view, there is no linear relationship. Okay, the relationship is not going to be linear. It is going to be polynomial. It's going to look something like this. Over a period of time, as the height increases, weight increases. After a certain point in time, your height does not increase. After 18 years of age, you don't get any increase in height. 18 to 21, I believe. I don't remember the exact number. But if I remember my school level, it's a biology clearly, after a certain point in time, right? After a certain point in the time, which is age, there is a third factor over here, which I've not considered in the analysis, but I have to take that in account. After a certain point in time, my height is not going to increase. So if my height is not going to increase, I don't think my weight is going to increase, because my bone density is not increasing, right? But my weight may even increase, right? Even if my height is not increasing, because I might be eating a lot, and hence my weight is increasing, right? So there can be one line like this, and there can be one more possible explanation, which can be something like this, right? There can be multiple explanations to the curvature which the model is going to take, but that is one thing that I can conquer. This intercept will be zero. If there is no height, there is no weight, right? If there is no height, it means I'm not born. If I'm born, I have a height, right? If I am a single cell organism in my mother's womb, right, where I'm actually getting grown up, right, for the next 9 months, I'm going to grow in there, and then I'm going to come out in the live world, right? By that time, when I'm actually born, when my mother has conceived me, okay, at that point in time, my height is zero. I'm just a single cell organism. From there, I'm going to divide. My cells are going to divide. Nucleus is going to divide. Then I'm going to become a human being. At that time, my height is zero. Hence, my weight is zero, right? Or or maybe conceptually height may never be exactly equal to 0, close to 0, and hence the weight is also very, very close to 0. But this is a possibility. So in a context like this, it is really possible that theta 0 is actually equal to 0, right? So I have taken this decision, if you know what I mean. If you see what I was doing, what I was trying to discuss, I've taken this decision basis my business understanding, right? The business understanding with respect to predicting or estimating sales, with respect to giving money to TV advertisement is one thing, and looking into height and weight of individuals like me or yourselves when we are just born is another different thing. So basis the context, I have to take a decision. It is not that I'm simply going to look at the numbers, right? And I'm going to say the second model is best, right? Because both my constant and my variable is actually doing good. Okay, but hey, if I go back to my first model, it's quite clear that in the first model I can clearly see, right, that there is no need of the constant anymore. Hence, obviously, mathematically speaking, this is actually a better thing, right? But I cannot take a mathematical decision here. You should not be taking a mathematical decision. You should always be taking into account the business context, right? So I can write, okay, comparing both the models, I come to a conclusion that I come to a conclusion I have written, right? I have not written we, I have not written we can come to a conclusion. It is my conclusion. I'm doing this analysis. It is me. I'm doing this analysis basis myself. This is what it is. And I'm going to defend it. Okay. Mathematically, the model we got after scaling the training data is better since it does not have an intercept, right? However, pragmatically, or I can also say practically, the second model relates to the given business problem better. Okay, hence we may want to choose the second model, right? So this is one thing. Okay, this is how we have performed one type of scaling. Okay, I can share examples of WinMax scaling as well. You can try it from your end, and you can try to see, maybe you can take this as homework. Okay, try to see how min-max scaling is done. You can take examples from sklearn, or you can ping me, I'll tell you how to do, and you can try to execute this code again. Okay, which part? Okay, this part. Okay, try to do this portion number 6 and portion number 7. Okay, now what you can do is, rather than using this object for standard scaler, okay, rather than using this for standard scaler, you can use the min-max scaler. Okay, try to create a min-max scaler thing, and then you scale the data. Okay, you train the scale, you scale the training data, and then you can look at the mean and the standard deviation. See how it is going. Right, see how it is going. In this case, we have got a normal distribution. In min-max scaling, are we going to get a normal distribution? I doubt, right? Because so mathematically, that is not the property of min-max scaling. And then you can do this. Okay, again, you can try to use. I would suggest using stats model because it gives a very good regression results kind of a tabular output. This is really nice. It clearly tells us what is going on in the background, especially this section, and then also the section which you see over here, right? So try to do this as a homework. You can download the notebook from our LMS. I'll ping in the group once I've uploaded it. So using the data set, first of all, you can go to this cell option over here. Go to the cell option and you can run all the cells. So all the previous code will be executed, and then you can try to do this exercise and try to compare it with the previous one. Okay, so try to compare your model where you are doing min-max scaling, right, with the old model, right? You try to understand what kind of differences you are getting, right? I hope until this point it is clear. Is there any questions until this point in time? I'll take that as a no, right? Okay. Then let's have a stop here. I believe we are almost also closer to the time. We will stop over here. From the next class or the next session, which is let's say tomorrow, we will be using another data set now. Or maybe what we can do, we'll start with this one only. We'll take this data set only, and we will change this headline from simple linear regression to multiple linear regression. Right? We will follow same kind of a life cycle. Okay, we are again going to do some quick analysis. We'll import the data, same data we are going to import. Then rather than doing all this add constant and all those things, which we did because we were doing simple linear regression, we are going to do multiple linear regression, right? But please note, in multiple linear regression, it is actually better to use stats model. But that is not to say that we cannot use OLS. We can use, okay? We can actually use OLS in case of multiple linear regression as well. We are going to look at that as well. And then we can try to fit the regression model. Actually, I will obviously prefer using uh, uh, the scikit-learn thing. But why I am also trying to look at this OLS thing is because of that output. Okay, that's the best thing I like about OLS. OLS clearly tells you. Okay, the stats model package clearly tells you this is what I've done, and that's what I found out. That's why I have come to this conclusion. This is the intercept. This is the coefficient. Right? Let's do that in the next session. I'll stop the presentation now. If you have any doubts, please let me know. Yeah, please do let me know if you have any questions. Thank you so much. Good night, friends. Thank you.
Thank you.
Thank you.
Thank you.